So here I have two functions, one of them being x and one of them being sine of x. And you'll notice that if I zoom into this area right here, we can make some useful conclusions. So when you zoom into this circle right here, x will remain the same general shape, and that makes sense, right? Sine of x will have some kind of curving feature, right, like that. So we could say this point right here will probably be the origin, right, just like here. And if you zoom in even further, you'll notice that x still has the same shape, the same general shape, a straight diagonal line. And sine of x will start to look more and more like a straight line. It won't be completely a straight line, but you can see that sine of x is starting to look kind of like a straight line, right? And if you keep zooming in, well, you'll notice that sine of x will begin to look almost identical to x. If you zoom in far enough, it'll be almost impossible to tell the difference between these two lines. These two lines will look essentially the same. So why is this useful? Well, this helps us determine the limit, or intuitively determine the limit as x approaches 0 for x over sine of x. And we can use this to our advantage, because what do we know about when you have a limit and you have a function divided by a function? Well, that just means that this is the same thing as a limit as x approaches 0 for x over the limit as x approaches 0 for sine of x, right? That's one of the fundamental properties of limits. And what are these two actually saying? They're saying that where this is the point 0, 0, right? As x is getting closer and closer to 0, what is y approaching? Well, because these two are essentially the same thing, almost nearly the same thing, and especially the closer you zoom into it, the more they are like each other, we can say that their limits are also like each other because their general structure is very, very similar. So their limits must be very, very similar, right? So we can say that the limit as x approaches 0 is something. But we know that because sine of x is almost identical to x, when you zoom in far enough, we can estimate and say it's also about equal to something. And we have something divided over something. Well, that's just equal to 1, right? Something divided over the same value is 1. And this is how we derive the first very useful formula for trig functions, where the limit as x approaches 0 for x over sine of x equals 1. So now that we have this useful formula here, we can also assume that the limit as x approaches 0 for sine of x over x equals 1. And that's because, remember, this is 1 simply because these two values turn out to be the same thing, right? When you take the limit of both of them. So that means that if you switch them around, well, it still simplifies to 1, right? Because they're the same values. So using this formula, we can actually derive the second formula that's very useful for solving trig functions. And that's the limit as x approaches 0 for cosine x minus 1. And to do this, to figure this out, first I'll attempt to do some simplifying. So I'm going to multiply this by cosine x plus 1 over cosine x plus 1. And you'll see why I'm doing this after I finish. So this simplifies to the limit as x approaches 0 for cosine squared x minus 1, right? Which is equal to x times cosine x plus 1. And remember that there is a fundamental trig identity. It's that sine squared x plus cosine squared x equals 1. So if I subtract 1 from both sides, right, and then I I subtract sine squared x from both sides, what happens? Well, here on the left side, I get cosine squared x minus 1 equals negative sine squared x, right? So I can just rewrite this top here as the limit as x approaches 0 for negative sine squared x over x times cosine x plus 1, right? And this can be rewritten as limit as x approaches 0 for negative sine x over x times sine x over cosine x plus 1, right? And guess what? What can this be rewritten as? Well, another fundamental property of limits says that this is just negative 1 times this. So we can just rewrite this as the limit as x approaches 0 for negative 1 times the limit as x approaches 0 for sine x over x times the limit as x approaches 0 for sine x over cosine x plus 1, right? And now, when calculating these limits, well, we know that the first one is just negative 1 because it's a constant. The second one, well, this is just the formula, right? The limit as x approaches 0, the limit as x approaches 0 for sine of x over x, it equals 1. And for the second one, well, we just use direct substitution. What is the top? The top is sine of 0, so that's 0. And what about the bottom? Well, that would be cosine 0 plus 1. And we know that the 1 we can just cancel out. We don't even need to solve this, right? Cosine 0 is 1, and then plus 1 is 2. But the top is a 0. So this means the final value is just 0. So we're saying that now we have a secondary formula, which is the limit as x approaches 0 for cosine x minus 1 over x is equal to 0. And you'll find that these two formulas here, or you could say 3 in a way, they will be very, very useful in solving trig identities. So I'm going to be showing some examples later on to help explain and to show how you use these formulas. So now let's do some examples. So the first one says the limit as x approaches 0 for sine of 2x over x. And I notice that this has similar properties to this first formula, right? But not quite, because this is a 2x and this is an x. So I'm going to try my best to make these two the same. And how would I do that? Well, I can simply multiply the top and the bottom by a 2. And the reason this is helpful is now these two are the same. I could even say that a equals 2x. And I could rewrite this as the limit as x approaches 0 for 2 times sine of a over a. And we know that according to the property of limits, we can just move any constant out. All right. And here we have the formula. The limit as x approaches 0 for sine of a over a, right? And a, they are the same thing. Yes, this is not x, but they're still the same exact thing. If they're the same exact thing, in this case it's 2x, we can still use the formula, right? So that means this right here is just 1. So it's 2 times 1, right? So just by modifying, rewriting the expression a tiny bit, we can use this formula to our advantage and get an answer of 2. Now this second example says, what is the limit as x approaches 0 for sine of 2x over sine of 3x? So here we have a problem. We don't have an x, right? We don't have a single x like we have here in this formula. So in order to help match this formula here, or this one here, what we're going to do is we're simply just going to rewrite this expression as the limit as sine of 2x over sine of 3x times 1 over x over 1 over x. And the reason this is useful is because now you can say the limit as the limit as x approaches 0 for sine of 2x over x over sine of 3x over x, right? And now it's still not exactly similar to these formulas because this is an x, this is a 2x. But this is just the example from last time, right? So all I have to do is multiply the top and bottom by 2. And I can do that because they cancel out and make a 1. And I can multiply the top here and the bottom here by 3. And what I get is this and this are the same. This and this are the same. And to make it more clear, I can say a equals 2x and b equals 3x, okay? So I can just rewrite this as the limit as x approaches 0 for sine of a over 3 times sine of b over b. And I can rewrite this as the limit as x approaches 0 for 2/3 sine a over a sine of b over b. And this 2/3 is just a constant, so we can move it out. And because this is a function over a function, we can rewrite it as the limit as x approaches 0 for sine of a over the limit as x approaches 0 for sine of b over b, right? So after doing all this rewriting, what do we notice? Well, this is a formula and this is a formula. They both satisfy this right here, right? And that equals 1. So what we have is 2/3 equals 1, or 2/3 times 1, which is 2/3. And I didn't have to go out of my way to set a and b equal to these. Just by recognizing that these two are the same thing, I can use the formula, right? But if you do want to substitute, it helps with understanding or better illustrating these formulas, right? Because this is very clear. This very clearly is the same thing as this. So the answer is 2/3. So the third example is saying, what is the limit as x approaches 0 for x squared over 1 minus cosine squared x? So just because you see a cosine x here doesn't necessarily mean you're going to try and manipulate this expression and make it look like this, okay? Because sine and x, sine and cosine, I mean, they have a lot of similarities. And I'm going to show you how to maybe manipulate this to figure out maybe if it's this or this. So first of all, whenever you see 1 minus cosine squared x or 1 minus sine squared x, you need to recognize that these two are part of the fundamental identity sine squared x plus cosine squared x equals 1, right? Like this appears all over the place. So that means if you know this, then you have to know 1 minus cosine squared x equals sine squared x, right? Or 1 minus sine squared x equals cosine squared x, right? So this equals sine squared x. So we can just rewrite this as sine squared x. And this is not exactly this identity, but if you notice that this is squared and this is squared, well, that's just the same thing as this times this, right? X over sine x times x over sine x, which is the same thing as the limit as x approaches 0 for sine x times the limit as x approaches 0 for x over sine x. And here we have something that satisfies our formula. So this is 1, and then that is 1 as well. And the answer would be 1. So this example asks, what is the limit as x approaches 0 for 5x over tangent x? And I know that I would want to rewrite tangent x in terms of sine x and cosine x because my formulas are, they have sine x and cosine x in them, right? And my goal is to try and manipulate the expression to match the formulas. So here I rewrote tangent x in terms of this, right? This right here. And I noticed that I have a sine x here and I have an x here, and they're on opposite sides of the fraction. So maybe if I do this, 5x over 1 times cosine x over sine x, right? I took this and put it out here. So this is a multiplication sign and this is flipped, right? So now I have my x, I have my sine x. What I want to do is I want to pair these two underneath the same fraction because that matches the formula. So what I'm going to do is this x is going to stay right here. I'm going to move this 5 over here. I'm going to move this sine of x over here. And now you can see that I get the limit as x approaches 0 for x over sine x and 5 cosine x, which is the limit as x approaches 0 for x over sine x times the limit as x approaches 0 for 5 cosine x, right? And this is the formula, so this is just 1. And if you do direct substitution here, well, this is just 5 cosine 0. Cosine 0 is just 1, right? So 1 times 5 times 1, and my final answer would be 5. The fifth example says, what is the limit as x approaches 0 for cosine squared x minus 1 over x times cosine x plus x? So we notice here that these do have cosines, and this is, well, there isn't really anything that directly represents this, right? So what I can do is I'm going to rewrite this as the limit as x approaches 0. And I noticed that this can be rewritten, the top can be rewritten as cosine x plus 1 times cosine x minus 1. And the reason I'm thinking this is because I have a cosine squared here, but nowhere in my formula does it say I need to have a cosine squared. So I need to find a way to try and make this cosine squared just a normal cosine. So what I'm going to do is I'm going to see if I can factor it. And it turns out I can factor it into this right here. And the bottom, well, we can just keep this here for now. Oh, and this is parentheses. And now it's still not entirely obvious. But I noticed that this x and this x right here, they can be factored out. Or let's just rewrite it here. So this can actually just be rewritten as x times cosine x plus 1, right? Which ultimately can be rewritten as cosine x plus 1 times cosine x minus 1 over x times cosine x plus 1. And we notice that because I factored the x out, these get canceled out. So now, because they got canceled out, I have cosine x minus 1 over x. And that is exactly my formula, actually. So because this is exactly my formula, I can just say this whole thing is just 0.